Let us start with probably finding out the basic equation that we are going to use for any variable mass system. So let me say that there is an object. Let us say that there's an object here. In this object, I'm going to call it the main object. This is the so-called main object. And this object has got a mass m and it has got a velocity v at some time. This is the velocity of this object at some time t. And there is a small mass somewhere. Let us say there is this small mass dm which is traveling at a velocity u. And you will notice that I have put a vector sign over v as well as u. So they don't have to really move like this. They don't have to move along the x-axis. They may be moving randomly anywhere in 3 dimensions. And as long as I use v as a vector and u as a vector and v as a vector, the job will be done. So let's say that there is this small mass, there is this main object. Their masses are dm for the small mass and m for the main object, and their velocities are v and u, and all this is happening at some time t. So let me define that this is some time t, and this entire thing, this mass, the main object as well as the small mass, this entire thing combined is my system. So this is the system that I want to analyze. This green thing is the system. So any forces that are acting between this small mass and this big mass main object are internal forces, and we are not going to use them in our analysis. External forces will have to be used up. And this is the situation at some time t, and what happens at a time dt later is that this guy dm maybe goes and it hits this guy m and it merges with it. So there is a completely inelastic collision, let us say. So what happens dt time later is that what we have is this guy. This guy has got a mass of m plus dm now, because that small mass has merged into the main object and it gives us this huge object. And as a consequence of the hit that is suffered by this guy big M has a change in its velocity. Let us say that is dv. So at this instant its velocity is maybe v plus dv, again with a vector sign on the top, so that we can deal with any kind of situation that arises. And this entire thing is at some time t plus dt, right? And let us then see what are the equations that we can write. So first we can say something about the initial momentum of the system, p initial, which I'm going to say is the momentum of the system at time t. So this is a function of time t, and this is equal to dm times u plus big M times v. So in vector notations, dm times its velocity, m times its velocity will give me the total initial momentum of the system at time t. Now what is the momentum of the system at time t plus dt? The momentum of the system at time t plus dt is going to be this total mass m plus dm. So you've got m plus dm traveling at a velocity which is v plus dv. So v plus dv here. And then I can figure out what is the change in momentum, because I know the initial momentum, the final momentum. So therefore the small change in momentum that happens in that small amount of time dt is equal to p at t plus dt minus p at t, which will be m plus dm multiplied by v plus dv minus, I can write this entire expression here. So I've got dm multiplied by u plus m multiplied by v. And what do I get? When I open up this first bracket, I'm going to get 4 terms. The first term is going to be m times v. So that's the first term. The second term is m times dv. The third term is dm times v. plus the fourth term is dm times dv. And I will just open up this bracket. There will be two terms and they both will become negative. So there will be minus of dm times u minus of m times v. And some things here will cancel out. You can easily see which are the things that are going to cancel out. There is a mv here with a minus sign. There is a mv here with a plus sign. So the first and the last terms are going to cancel out. And what else? This term, this is a product of two differential terms. So it's going to be very small. So I will neglect out this term. This term is not really going to cancel out, but it is going to be neglected. And then what do I end up with? I end up with the equation that looks like mdv, and then I've got a dmv and then a dmu. So maybe from this term dmv and this term dmu I can take a dm common. So I'm going to get mdv plus dm times v minus u. Okay, cool. Now I have found out the change in momentum of this entire system, the thing that I defined as my system, in a small time dt. So that will allow me to figure out what is the net external force acting on the system, isn't it? So what I can say now is that the summation of all external forces, which is the net external force acting on the system, is equal to dp divided by dt, the rate of change of momentum of the system, which will be, and because the expression for dp is already found out, I can just divide this expression by dt. So I can say that this is equal to m times dv by dt plus dm by dt times v minus u. This is what I've got. And I just then rearrange this equation in a certain way. What I do is I invert the signs inside this bracket so that the sign here will get inverted. Once the sign here becomes minus, I will take this entire term to the left hand side, and then I will have just this term on the right hand side here. So the entire sequence of steps will be summation of f external is equal to m dv by dt minus dm by dt times u minus v, inverting the signs there also, and then bringing this entire term to the left hand side. So I get summation of f external plus dm by dt times u minus v is equal to m dv by dt. And then I see that this term u minus v has got a special significance. Suppose I go back to the previous figure. I go back to this figure and I ask you, what is the velocity of dm with respect to m? Right? The question is, what is the velocity of dm with respect to m? And I can figure out the answer here. Velocity of dm with respect to m is going to be velocity of dm with respect to ground, let us say, minus velocity of m with respect to ground. And I know both these velocities. I know that the velocity of dm with respect to ground is what I have taken as u, and the velocity of m with respect to ground is what I have taken as v. So these are the velocities with respect to an observer that is standing somewhere here, let us say on the ground. So I have got this as u minus v, which is exactly the term which I have here. So you see that I have got a u minus v here and I have got a u minus v here. I call this term as v relative. V relative. And then I can rewrite this entire expression as, so therefore the final equation becomes summation of f external plus V relative times dm by dt is equal to m dv by dt. And this is the equation that we are going to use. So let me box it also. Let me put a box around this equation and then explain to you the various terms. So when you have a look at this equation, you should keep in mind that summation of F external is the net external force acting on this entire system. So that means I should include all the forces acting on the main object as well as all the forces acting on this dm small mass, but they should be external. That's one. Second is I should use VREL, which is the velocity of this small mass with respect to this main object, and which will be obtained as u minus v, which, because we are using vector notations, is going to be the right term to insert here in this equation. So if you find VREL properly and if you insert it here, then you cannot ever make a mistake. What is this guy dm by dt? So if you look at dm by dt, you will see that if you only look at this guy, if you only look at this main object, then the mass of the main object increases at the very next moment. Now the assumption here is, if I'm dealing with a variable mass systems, then the mass of this main object will keep on continuously changing. So maybe at this moment, from t to t plus dt, this guy dm comes in and it is absorbed by this main object. But from t plus dt to t plus 2 dt, somewhere here, another mass dm may come in and it will be absorbed by the main object. So the rate at which the mass of main object changes, that's dm by dt. That is this guy. And m is the instantaneous mass of the main object, and this guy dv by dt is then the acceleration of the main object, because you see it's the main object that is moving here with a velocity v, and here it has got a velocity v plus dv. So this is the acceleration of this main object. So what is going to happen is, in all the variable mass system problems, you are going to use this equation where you will have to define a proper main object. Most of the thought process will go into defining what is the main object, and once you define what is the main object, its instantaneous mass will come in here, its acceleration will come in here, and the rate of change of mass of the main system will come in here. VREL will come in here. VREL will be found using vector notations, so whatever is the sign that you get, you have to insert it here, no issue. So you will easily understand that we will have to first of all create a coordinate system, and we will have to assume I cap, j cap, k cap, so that we can give signs to forces and signs to VREL and to this dv by dt term, and m will be filled in here, so no issues with that. But what will be the sign of this dm by dt term? So keep in mind that this term dm by dt is taken as greater than 0 or positive if mass of main object increases with time, and conversely dm by dt is taken as less than 0 or negative if mass of main object decreases with time. And what is the interpretation then of this term? Because the term on the right hand side shows you a certain object and its net acceleration, so the left hand side should be some kind of force. We have got forces here, but there is also this term. So what kind of a force does this term represent? So when we interpret this term, what we find out is, maybe this term is the force that is exerted by this guy dm when it is interacting with this guy m. So if u is more than v, let us say, just to think about this situation in a very simplified one-dimensional format. So let's say they are indeed moving along x-axis like this, and v is less and u is more. So when this guy dm with a greater velocity comes in and it is absorbed by this guy main object m, then what's going to happen is that this guy dm is going to exert a pushing force on m, and this term here represents that pushing force. So we will give a name to that term. We will give a name to that pushing force that is applied by dm on this m as it goes and hits this guy m, and that pushing force is often called a thrust force. So please keep in mind So this dm will either go and hit this mass m, or it will be ejected from this mass m, and because of either of those two things happening, there will be a force acting on big M, and that will be vrel dm by dt. Mostly whenever we are dealing with maybe rockets, we will call this guy the thrust force. So vrel into dm by dt is sometimes called the thrust force. Let us keep that into our mind. And you see that this is a very simple equation. So I think the next thing that we should do is maybe try to go and see how to use this equation effectively.